that we have that capability. No
Please
pressure.
don't. Okay.
Sorry to spring that on you.
I'm going to sit over there.
No, you're good. So just disclaimer, I'm going to have no idea what I'm talking about, but I'm going to talk about it. Okay, so wait, is this slideshow? Okay. Also, Joan, feel free to like cut me off if I'm going too long. Okay, so variational quantum algorithms today. So first, we're gonna give you a little bit of a gentle introduction. Okay, so POV, you are a quantum algorithm. Let's say you're Shor's algorithm, and you want to crack Roblox state-of-the-art RSA encryption, so you can get some Roblox. This is Roblox for whoever doesn't know what it is. I'm sure most of you do. And this is RSA, and you're gonna break it to get some Robux. Okay. So what you're gonna do is you're gonna try running your algorithm. Your computer is gonna complain because you don't have enough qubits. It's not gonna be like connective enough, and you also cannot support the circuit depth of a Shor's algorithm. And you're gonna be sad. So now your dreams are crushed, and you'll never be able to like beat your sister in whatever this is. Adopt Me. I just found the most popular game on Roblox and put it there. But all hope is not lost, right? Because I've got a solution for you. Introducing variational quantum algorithms. So what are VQAs? We can basically just like boil this down to being like machine learning but quantum. And what does that mean? That means that you have a quantum computer, like as you can see from this diagram. This acts as your like so-called machine learning model. You basically give it something, it's going to spit out something, and you're going to use this classical optimization thing to kind of update the weights of these parameters. For those of you that don't know how machine learning works, that's basically just like, basically the machine kind of learns to output like something specific, and it does so by doing this like iterative process that we're gonna go over very shortly when we talk about its parts. And so the advantage of variational quantum algorithms is that it has shallow depth. It is noise tolerant, unlike the Shor's algorithm that I introduced earlier, because it's like shallow depth. And here are some of its parts, which we're going to go into detail in a little bit.
And just to hop in and interject on this slide, which is perfect and drawn from the paper, we should take all of these claims as propaganda. We actually are, the lot of the research that we're going to be doing is going to be interrogating, really, are these things noise tolerant? I think I have cause to believe they may not be. Can these things work in shallow depth? Because this is how these algorithms are marketed. And one of the core topics that you encounter in quantum ethics when you talk about societal impact is quantum technologies, which are vastly overhyped. And I think VQAs may fall into that category. Sorry, Jeff, you're doing fabulously. Keep going.
Yeah, I do talk about a little bit about the noise thing at the end, but anyways. Okay, so first we're going to talk about the cost function. Joan did not get this meme, and I don't either because it doesn't relate to the title. It just has the word cost in it. Anyways. So what is a cost function? So essentially what a cost function is, it's something that kind of encodes how well the model is doing. And this is, in a more abstract term, this kind of defines something called a cost landscape, which is basically like, you can think of this like landscape, this hypersurface, which the optimizer kind of tries to find its global minima. And the global minima is supposed to correspond to like the optimal solution for the algorithm. And for those of you that don't know what a hypersurface is, here's a surface in 3D. Just think this surface is now in like 7D or whatever, like some high dimension. And here's kind of how the paper like defines the cost function. In general, it is made up of like this like function. So basically you give it some inputs and some observables, which is kind of like your output, and you also give it your model, and it spits out a number or a tensor or whatever. And this tensor kind of like tells you how well your model is doing. And the lower the score it is, the better. And so your job is to kind of like find the minimum value that this cost function can take. Here's an alternative formulation that I don't get, so I'm going to make Joan explain it. But it is supposed to be very convenient. Anyways, moving on. Onsets.
Hey, Jeff, I can clarify that.
Yes.
function piece for a sec. If you
Okay.
can see the blackboard. So that
Barely.
equation on the right, nobody uses that form. It's just the form that they put in the paper. It's just that equation is just the authors trying to be as general as humanly possible. But in reality, in most of the things we're going to see, the cost function actually has like a nice little equation with a nice interpretation. So cost function, which depends on your parameters. Is this viewable on the blackboard?
Yeah, I think so.
More or less?
I think it is flipped. Is it flipped for us or for you guys?
But people can see what I'm writing.
Yeah.
Point. Okay, so the cost function is just defined as the expectation or average value of some special operator. And I realize I'm using theta and O to mean two different things. So we'll call O hat the operator. And this doesn't look anything like that equation there. That equation there can basically just be boiled down into adding up a bunch of different expectation values in case you had a bunch of other operators you might want to use. But for the most part, we'll identify a single observable that will just calculate the expectation value by taking.
Oops, I got kicked from the meeting.
Really? Oh.
Yeah, my internet's bad. Sorry. Maybe just.
Like your screen share stopped?
No, I literally just like disconnected and reconnected to the meeting.
Oh, okay. Cool.
Sorry, continue.
So this expectation value is just calculated like in the normal way. So I may be glossing over some details. People in the room might have different, types of background. But you could think of this whole process as just preparing a quantum state, which depends on that angle. And then you just calculate the expectation of the value of the operator with respect to the state you prepared. That's going to give you a number. It's going to be between 1 and 0. This number is your grade. If you're minimizing, the best grade you want is 0%. If you're maximizing, which is just the same problem, the best grade you want is 1. So it's going to spit out some number which you could think of as your percentage for how well you did. And so, like, again, that equation is intended to be hella general, and it's generally more complicated machinery than we really need. Just think of like what you are optimizing is the average value of some observable. When we say observable, what do I mean? Energy is an observable. So one of the most famous of these algorithms minimizes energy. And that's what the cost function is saying. So keep that energy picture in your mind if this is starting to feel a little bit abstract. And Jeff, you can go ahead.
Yeah, I'm gonna add that to my slides eventually. Okay.
That's
Anyways,
the
so
simpler
we're gonna talk
version
about the
I
Onset
was
now.
referring to before.
Yeah, I know, but anyways, so the Ansatz is a German word. I forgot what it means, but it's basically like the meat of the VQA. So you can think about it as like the actual circuit that does all the like magic that really happens. And so the structure of the Ansatz is really task specific, or it could be task specific, which people call problem inspired Ansatz, or it could be general, which is like problem agnostic. And problem inspired Ansatz kind of like exploits like the information about a problem to kind of tailor the ansatz to better suit its needs. And problem agnostic, as the name suggests, can be like basically applied to anything, and it could be a good starting point. And in general, an ansatz could be expressed generally as like this product of sequentially applied unitaries. Unitaries are matrices, and this is like kind of the equation. So it's basically, you can think about it as like having multiple layers. Each one of this U is this like weird product looking thing, which are made up of something called gates. And gates are themselves like matrix operations. Here's a kind of more pictorial diagram of what I'm talking about. So this thing is an ansatz, which is broken up into layers, and each layer has like gates. Here are some examples of common ansatzes. There's this thing called a hardware efficient ansatz, which attempts to minimize circuit depth in order to avoid barren plateaus and all these other problems that come with having a deep circuit depth. This is a problem agnostic architecture because it doesn't really like, it can be applied to basically every possible problem you can find unless it doesn't work and you have to change it. it uses hardware specific gates. And what that means is that there are some, like for each specific quantum computer you're running on, there's a set of gates that is more suited towards that hardware. And if you want to run other gates on it, you'd kind of have to like break it down to a sequence of like other gates in order to run it well. And so the hardware efficient onsets basically is machine dependent. So each machine kind of has its own like hardware efficient onset. The advantages of this is that it is very versatile because it can encode symmetry and like step reduction, all these things, and it's also useful for studying Hamiltonians. The disadvantage is that, according to the paper, is that the random initialization strategy may lead to Baron plateaus. There are some other onsets mentioned in the paper, which I didn't explain because I don't get, but here are some names if you want to look into them. And here are some from
just a quick clarification. This is all great, and just to connect it to what I said a minute ago about the circuit preparing this theta dependent quantum state psi. The ansatz is the circuit that prepares psi. So you have some theta dependent quantum circuit, and then given your starting state, it will prepare psi of theta.
Yes.
And you said you
and here are just some.
Sorry. Ansatz is German for guess. So what an ansatz is just a guess of how you're going to get to the state you want. And that's why there's a lot of freedom in which ansatz you choose, because it's just a guess and people have different ways they'd like to try and go about it.
Yeah, and again, here are just some like diagrams that I found from your guys' papers. As you can see, they all kind of vary in architecture, and that's because each task has its own like, I guess, guessing method that's like more suitable for that task. Anyways, so next we're going to talk about the gradient. So before we talk about the gradient, in general, how do you find the minima of a function? Here's one way which you may have learned in calculus, where you basically just, you see a function, you set the derivative to 0, and it's probably like some kind of minima, or it's an inflection point, in which case you're screwed. But closed formulas for gradients in general are hard to find. If you take anything that's beyond high school math, you'll probably know. Like there's some equations or there's some solutions which don't really have a closed formula. Here's another way you could do it. So consider the gradient again, like at any point, like which is just basically a number. The gradient kind of like, if you take a multivariable calculus, you know that the gradient points in the direction of steepest descent. What does that mean? What if you look the other way? You're going to actually be looking at the direction of steepest descent, right? And so what does that mean? If you travel along that direction, you'll eventually end up at some sort of minimum. And this is what this illustration is illustrating. I just said illustrate twice. So in classical machine learning, this algorithm called gradient descent is a way to iteratively find this minima of a cost landscape. And in quantum, I don't know how this works, but this thing called parameter shift rule, you could use to classically like estimate the gradient of an ansatz. There are also other, this is kind of the formula they gave. Again, what is going on? But there are other gradients available, including like second order methods, which is even longer, so I didn't include them in the slides. Okay, next we have this thing called an optimizer. Again, this has nothing to do with optimizers. But so, as I said earlier, gradient descent kind of like iteratively steps in the opposite direction of the gradient, and this kind of descends towards some sort of minima, right? But the issue is that finding the global minima of a cost function is usually NP hard. What do I mean? So if you go back to the diagram, wait, where's my cost landscape? Whatever. Okay, let's say you had like a function kind of looks like this, and then like there's another part to it. The gradient would kind of like point in some sort of minima, but that doesn't necessarily mean that it's the minimum of the entire function. It just means it's like minimal at that particular location. And that's kind of a problem because you want to go towards the global minima, but usually you can't really find that. And there are new challenges associated with quantum algorithms, including this like hardware noise, Baron plateaus, this like stochastic environment, whatever. And so what do we do about that in quantum? I don't know. Here are some popular optimizers. I'm not going to go into detail. We can revisit these later, but here's one that's from machine learning, and here are some other ones that the paper introduced. Anyways, what are some applications of variational quantum algorithms? Here's a nice handy breakdown by Joan. As we can see, machine learning is a big part, is a big one. Quantum simulation, optimization, chemistry, I don't know what does that even mean? Anyways, so in quantum chemistry, there's this thing called a VQE. Okay, sure.
You're being very patient with me. I appreciate it. Quantum information applications are like, it's like a chicken and egg thing. I'm actually quite salty about this. So getting to run one of these algorithms to do something on a quantum computer is already very sus. It's very speculative. Like maybe it won't even happen. And what quantum information applications are saying is they're assuming you already have a quantum computer, and then you're using the variational quantum algorithm on a separate quantum computer to help your first quantum computer. But like you need a working quantum computer before you can do this. So I consider those applications to be extra sus because they basically like require that quantum works before you can use them to help quantum to work. If that makes sense.
It's like, are you bored? Just get
Got it.
one.
Yeah, exactly.
Okay. So in other words, this is the non-sus category and this is sus category. Moving on. So this is a thing called a variational quantum eigensolver, which is very useful in quantum chemistry. What it does is, I'm sure you all know about it, but I'm gonna briefly explain again. It estimates the ground state energy of the Hamiltonian, which you kind of give it. And the cost function is the expectation of this over some trial state. And this is what Joan talked about earlier, right? Where you give some random state, you pass it through the onsets, and then you kind of take the expectation value of that. And you want to minimize this. So there's no optimal onsets like that the original paper talks about, although some people use this thing called UCC. So in math, there are many applications such as VQAs, which Indy can talk more about. What I understand about all these algorithms is that they solve things faster. Anyways, in machine learning, the QGAN, which is the quantum generative adversarial network, is supposedly useful for like loading quantum distributions, and this is also supposed to kind of solve the problem of QRAM, which we can talk more about later. The CNN is, well, in classical like machine learning, it is a very useful model in computer vision for kind of classifying images and doing like computer vision stuff. In quantum, you can also use it for image recognition, but you can also use it for error correction and many other applications. And according to this paper that paper cited, it doesn't experience barren plateaus, which we can probably verify. And there are other machine learning tests such as classification. This is actually pretty cool. Like there's a class of classical machine learning algorithms that's called tensor neural networks that kind of draws inspiration from this like tensor product structure of quantum algorithms, and that can be exploited for classification because it's not linear. And there are many more. Okay, here are some challenges with variational quantum algorithms. Although like we've kind of painted them up to be like really great and like can exhibit quantum advantage in the near future, there are still challenges associated with them. Here are the three that are mentioned in the paper: trainability, efficiency, and accuracy. And we're going to go over each one of them separately. So trainability. Yeah, we all know about this. We're going to move on. So the next problem is efficiency.
I don't think everybody in the room knows about barren plateaus.
I thought you explained it, Joan.
Not to everybody in the room.
There's some new people.
There are some new people.
Fine. Okay, fine. So basically what happens is you have this thing called a cost function. We talked about that earlier, and that kind of measures the model's performance. But when you kind of scale up quantum algorithms, if you add more like layers to it, or if you like add more qubits, the cost factor kind of becomes like really flat. And when it becomes really flat, any gradient you take is going to have a value that's like basically 0. So it's not going to be able to descend anywhere, which means you're not training, which is bad because you want to train. You want to get to some kind of global minimum. Is that a sufficient explanation?
That's perfect. Yeah, great job.
Okay, cool. Okay, so efficiency is another problem that we have to consider. Expectation values, like to be able to calculate that is actually pretty inefficient according to the paper. Some possible solutions mentioned by the paper are buzzwords. Yes. And the next problem is the problem of accuracy. So when you have hardware noise and all these other stochastic like problems, like it can actually slow down training and also bias the cost landscape. The problem with biasing the cost landscape is that the global minimum of the cost landscape will like not like it may like not correspond to the actual like optimal result that you're looking for, and that affects accuracy and may also actually induce barren plateaus. And so error mitigation is important, and I guess this ties back to what Joan was talking about earlier, the problem with like hardware noise and all these other noise that kind of like still affects VQAs, even though we kind of market them to be more noise tolerant. Yeah, that's basically it.
Okay, let's thank Jeff. Great job. And I'm going to stop the recording, and now we can kind of transition into questions and discussion.